The last thing I want to deal with in this discussion of the Fourier series is just different ways to write it down. And this can be really useful because there are different nomenclatures you see in different books, and so just to see this and be familiar with it can be very helpful. And also it helps us on the development of the Fourier transform, which is coming next. So going back to the Fourier series now, which is this thing with the constant term out the front, so not the expansion in standing wave basis, but the proper Fourier series. And we derived this earlier. We have this constant term out the front and these coefficients for the cosine and sine terms given by this. Okay, one change we can make is to change everything to angular frequency. So get rid of nu naught and change it to k, and we get rid of lambda and change that to k as well. And if we do that, we get a Fourier series that looks like this. So now we have the ANs and BNs given by this equation here, and we've just eliminated basically the lambdas and nu naughts and just changed it all to this spatial frequency k naught. If you prefer functions of time and angular frequency, it would look like this. Now the role of omega here is exactly the same as the role of k. So omega here is the angular frequency in time. K is the angular frequency in space. So if you have some function of space, this is its frequency in angular units. You have some function of time, this is its angular frequency in time. So there's the Fourier series in angular units. Okay, what else can we do? Let's start again with now our angular spatial frequency Fourier series with these definitions of the coefficients. And we can combine, if we wish, the cosine and sine terms into a single harmonic function. We can do that because the cosine and sine functions here for a given value of n have the same frequency, and a cosine function plus a sine function can be written as a single harmonic function with some new amplitude and phase. In other words, we can write it like this. We still have a constant term out the front, but now instead of having a sum of sine and cosine terms, we can make it a sum over cosine. It could be sine, but I've chosen to do cosine here. And the definitions for AN and BN are related to the RNs and phi-n's, like this. What else can we do? Starting with our angular frequency expressions again, like this, we can redefine the summation to include positive and negative values of n. So the sum here is going from 1 to infinity. Well, we can define it as a sum from negative infinity to plus infinity. And in this case, we eliminate the constant term out the front because that's now taken care of by the n equal to 0 term, because when n equals to 0, this cosine is 1, and the sine term here becomes 0. The expressions for an and bn are these integrals here. So instead of k on pi, as we have here, we have something which is k on 2 pi, so it's half as big if you like, and that's because we're getting frequency terms from the positive and negative parts of this sum. So we need half the amplitude for each. They add up, the positive and negative frequency components add up. We also can note that there's a relationship between the little a's here in this half sum compared to this positive negative sum, relationship between the little a's and the big a's and the little b's and the big b's. And the nomenclature here is that the a negative n and b negative n are the coefficients for negative values of n, and the pluses here are the coefficients for positive values of n. So for example, little a n would be the sum of big A for negative for the positive value of n and the negative value of n. Okay, there's one last thing we're going to look at. Starting with this expression now, where we're going from negative to positive infinity, we're going to make three changes. The first is we're going to move a factor of 2 pi. So this factor of 2 pi here, which is in the ANs and BNs, we're going to bring that out the front of the summation. The second change is we're going to change the interval of integration, not its total length, but just move the offset so that it's symmetric now about the origin. So it used to be from 0 to 2 pi on k naught. Now we're going to integrate over the same distance but symmetrically about the origin. And finally, just to make our nomenclature a bit easier, every time we have an n times k naught, we're going to call that kn. Making these three changes, we can write the Fourier series like this. So here's our factor of 2 pi out the front. Our definitions of an and bn have changed a little, and we get this expression here for the Fourier series. Now, we can rewrite this, if we wish, in exponential form. So we can, because we've got a sum here of a cosine and a sine, we can also recognize that something like e to the I knx can be expanded as a sine and a cosine. The expression for cn here, in terms of the a and the bn, will be this. So if we expand this exponential term here, we will get a sine and a cosine. The sine will be imaginary, and so we make sure we have a minus I here to turn the sine function back into a real term. And the cn's then will be given by this integral here. So instead of integrating separately over the cosine and sine function, we can write it down as a single integral over a complex exponential. And if we expand this complex exponential, we get the sine and cosine sine and cosines back again. So this is something you can prove to yourself just by expanding these complex exponentials and seeing that this expression here is the same as this expression here. Now in the time domain, we could write this like so. So here we have omega n is n times omega naught, and the omega n's and kn's here play precisely the same role, depending whether you're in the space or time domain. Now, this last couple expressions here are really important. We're going to use them to develop the Fourier series in what's coming. So the reason why I've gone to all this trouble moving these factors of 2 pi around and redefining everything in terms of complex exponential notation is because this is the thing that we're using to set up something called the Fourier transform, which is a generalization of the Fourier series where we take the infinite sum and turn it into an integral.